So in this recorded lecture, it's part 3 of chapter 4, right? Moving charges and magnetism. So in the part 1 and 2, you would have seen about Barrett-Severt law, its applications, and next part 2, you would have seen Ampere-Circuital law and a bit of analysis of that as well on applications like solenoid, right? So this part discusses about moving charges in depth. So I would want you to open your notes and write the different formulas that we will discuss throughout so that you can start solving numericals if you have the collection of all the formulas in one pages. So moving charges, when you know that in this chapter the charges are moving, they are not static, they are not at rest like in chapter 1 and 2, right? So when there is movement, anything that moves, there is force also that is exhibited on it, right? So this specific part of the chapter is going to deal with force due to a moving charge. So when you're talking about force, we generally consider a conductor, right? And this conductor's small length element, which is dl. You know that if you have this point x, at x you want to measure the magnetic field. You want to measure magnetic field at x due to this small element of the conductor. You know, something that helps you to do this successfully is Barrett-Severt law, right? So what happens is you just use r vector, right? And then you also have an angle that is between this conductor, and most important condition, don't forget, I has to be present in order to exhibit a magnetic field from the conductor, right? So what is happening over here, you have seen the Barrett-Severt law. You know that the magnitude form of the Barrett-Severt law is k idl sine theta by r square, right? So we are just going to make few changes to understand what happens. So this will become dB is equals to k will remain k itself. This will be dq into v sine theta by r square. So what does this mean? This means that this charge is of which nature? It's moving. So that means this at x, basically, let's assume there is a charge now. This charge, which is I've highlighted with red, is actually moving. So let's assume this is moving with some velocity v. So that v variable I have included, okay? And this velocity variable that I have included is actually velocity of the charge. So this is dq. That means this small charge from this small element. So this is the modification about what will happen if at this place it's the charge that is actually moving with some velocity v, right? This is how your Barrett-Severt law can be modified. You know that it was just not magnitude that we have discussed in part 1 regarding Barrett-Severt, it is also its vectorial form. So in the vectorial form, we have discussed dB bar, which is k cross product of dl and r by r cube magnitude, right? So this will also be modified now because of these variables, that is with the inclusion of velocity, right? So we will use this as k q v bar into r bar by r cube. So this is the modification that is done over here, and you know the meanings, I mean the variables remain the same. So what is happening, r is the same displacement vector that you have used or distance vector you have used, and instead of l, which was actually telling you the direction of I, which is this, right, for the conductor, in which direction is the I flowing, correct? So this, instead of I, we are using a v here. So v over here is velocity, because the charge is moving, it will exhibit some velocity in some direction. So v cross r. Okay, so these two formulas I want you to write in your notes. From this only we will start this part. And I hope you remember in part 1, so as I told you, this dl was telling you about the current direction and r is displacement vector, right? So it's about the direction of the current with r, which will actually give you what? This will tell you about the magnetic field, right? This is cross product rule, chapter 4, grade 11, where I would have told you in your part A as C is equals to A cross B, right? So C is basically the magnetic field, and you will get to know if your four fingers are in direction of A, which means current, and then you curl it With what? You will have to curl it with. So B is the R vector, right? Which is here. So I would have told you that four fingers, if you align with this current, right? This is the current. And then while aligning these four fingers, you have to curl it towards the R, right? So your thumb will show inside the screen or inside the book or inside the whiteboard. So at that point of time, the magnetic field will be inside. So this is what we have discussed. You can use cross product rule, or else I would have also told you about right hand thumb rule as well. So both are applicable, but these are the formulas that we get when you are involving that this charge is actually in movement, in motion, so it will have some velocity, and that is how the Biot-Savart law will be modified. So since this discussion is extensively discussing about force, right? It's talking about force. So how do you measure the force on a single charge is what we will be discussing, which will be equals to Q V cross B. So that means over here also you can use a cross product chapter 4 grade 11 rule again. You can just C is equals to A cross B. So A is my force, sorry, C is my force, A cross B is V bar cross B, right? So what does this means? That means your four fingers of your right hand you can use for the direction of velocity, and you have to curl it to the magnetic field to know the direction of force. Whose force is this? The charge that is moving. Okay. So this is primarily the direction version of the force, or I would say the vectorial, and you know the magnitude version will be Q VB sine theta, because this is a cross product. So this would be the magnitude version, this would be the vectorial version. You can just write F over here, right? So these are the two formulas that we need. They're pretty much the same itself. One is vectorial and one is magnitude. So you have to use cross product rule over here. If you have put your four fingers in direction of velocity of the moving charge and curl them towards the magnetic field inside or outside, you will eventually end up getting the direction of force, which is capital F. This force is actually applied, or maybe is due to the charge that is moving, right? So that I have told you that if you take a conductor wire, for example, you take a small dl element and you take that this charge is moving over here. So due to this magnetic field from the small element, how much of force has been applied on this charge in this magnetic field that is around is what we are trying to say, right? So let's understand what will happen to the path of this charge when it is actually entering that vicinity, or maybe that surface of a conductor that has current in it, right? Only then we will be able to judge and comment on the force that is there. So talking about the path of that moving charge, let's assume that this is a surface, and this surface obviously has current that is flowing through it, which is why it will exhibit a magnetic effect, right? Only the magnetic effect will be coming into the scenario when current is flowing. So I'm assuming that this is the magnetic field, and I hope you know that this is basically telling that the magnetic field is inside, right? Inside the screen for me, inside the book for you, inside the whiteboard if I'm doing it in the class, right? So that is the direction of magnetic field. So when this is the direction of magnetic field, and the Q charge which I have taken, which you also have seen in chapter 1 and 2, is basically entering from outside in this conductor or maybe a surface, right? So you know that when this will enter, it will have a velocity v. Remember that this is not inside the conductor, it is actually outside, and or else I can say that it is approaching. Right? Who is approaching? It's the moving charge that is trying to approach the surface of the conductor that already has current. By current, we've got to know that there is magnetic field that is exhibited, and now when this charge is approaching the surface of the conductor whose magnetic field is acting inside, at that point of time, can you come up with conclusions of which direction will force be in this case? So first most important condition, the moment it approaches, what will happen at that point of time? There is some transient period that is over here. So what I meant is, because the charge is coming from outside, right? It is not present inside the surface. So there is some transient period that it will undergo. So that means magnetic force is suddenly switched on at this position as the charge enters in the region where the field already exists, right? So due to this entry phase, the force will be a bit fluctuating. It will depend upon how the magnetic field is defined at the boundary, right? You can see the boundary of the surface, right? So force will increase gradually, and this could also lead in slight variation of speed as well, right? So this is going to explain us a type of motion, okay, which you can guess which kind of motion can that be. But before guessing that motion, can you give me the direction of force, which is very important, which we have to discuss over here? So let's rely on the rule that we have just discussed, right? You know, V cross B will tell you direction of force, correct? So use your cross product from grade 11. What you will do? You will use your four fingers in direction of velocity. When you use your four fingers in direction of velocity, at that point of time, curl your fingers towards direction of B. You can see that B direction is inside, right? Where is your force acting? I hope you're able to understand. So your four fingers of your right hand will actually align across V, right? I'm picking up the situation over here separately. So they should be curled. That means they should be curled at that point of time across B. You know that this is how B is inside, correct? So at that point of time, your thumb will point in the upward direction. So this is what we are trying to do. When your thumb will actually point out towards upward direction, this is your velocity, right? And this is your, you can say, force, which is in the upward direction. You know, in grade 9 we have told you that whichever direction is force, the same direction will be acceleration as well. So acceleration will also be in the same direction, right? So here you can say that, you can also sum it up saying like velocity is like this and acceleration is like this, and they have a 90-degree relation between them, right? We've got it from the product rule itself. With the help of four fingers placed in velocity direction, curling them up towards the magnetic field, you will end up getting the direction of force. You can pause the video. You can also try it with me, or else try it on your own for some time to understand how this force is actually directed in the upward. Okay, so now you can think about the other possibility also. That other possibility I can draw, you can say that this is a surface. Now here, instead of the magnetic field going inside, it's actually coming outside. So this is my direction for magnetic field coming outside. At that point of time, when your cube will approach with some velocity v, definitely it will also undergo some transient period during this, right? It will not enter, and all the parameters will not be having their maximum values. Things will fluctuate a bit when it enters from outside, because it is in the approaching condition. So at that point of time, what will happen, again using the same rule, your V should be, your four fingers should be aligning with direction of V. But right now you will have to reverse your hand, right? You will have to put your hand in upside down position, right, which is opposite to your normal alignment. And at that point of time, you will see that force is actually coming in the downwards direction. So this is velocity, this is how your thumb will direct the force, and in the same direction you will have acceleration. So I can draw V and acceleration like this. This is also 90-degree. In the previous case, when B was actually inside, at that point of time, your velocity was over here and acceleration was over here. So this is when B is inside, this is when B is outside, right? This is the direction of force or acceleration. They have the same direction, right? So what we can expect will happen to the movement of this charge. So this charge will undergo a circular motion. So circular motion, when it undergoes, I want you to understand one thing. that this is not going through a uniform circular motion. I hope you know that in grade 9 and 11 there was something called as UCM, which is uniform circular motion, and for that the speed has to be constant and the velocity will change because of directions, tangential directions at every point, right? So for UCM that is a condition. So that is actually not applicable over here because the speed will fluctuate due to the transient period as the charge is approaching towards the surface, which is why it is not uniform circular motion, but it is circular motion, not uniform though. Okay, so we can call, in this case it is circular motion, right? And now you can think about different cases. So for example, you can think about one more case. So the case that I have discussed with you so far is actually a case where V and B are perpendicular. I hope you have understood that they are perpendicular, right? In one case V and um, B V. That means velocity and magnetic field were perpendicular, right? This was one case where magnetic field was going inside when magnetic field is coming outside. This was the other case where V and A will look like this. This is what we've discussed so far. Now we are discussing what will happen if they are actually parallel or anti-parallel. So I hope you know that whenever they are parallel, they will be aligning across the same directions, which is 0 degree, and anti-parallel is 180, right? So these are the conditions that we use. So instead of imagining anything, you can just go to the formula of force, that is Q V cross B. Okay, and within that you can tell me the magnitude of this. The magnitude of this, I hope you know. Keep noting down these important formulas in your notes for solving numericals further. This is theta, right? So this has to be 0 and this has to be 180. You know, sine 0 degree is 0 itself, and 180 is going to be 0 as well. So this will fall out at f0 itself, right? So that is when V and B are parallel or anti-parallel for that matter. And at that point of time, what will happen? So here, how was the motion in the first case that you have discussed? It is circular, right? But not uniform circular. So remember that over here, the motion will be straight line. If I ask you why straight line, because see, why straight line? Because the charge is actually trying to approach the surface, right? So are you disturbing it at any point of time? No, you're not, because force 0 means you're not applying any sort of external force, and in your grade 9 Newton first law tells you if you're not applying any force, the movement of the object will not be disturbed. It will retain as usual, right? You will have to stop it or maybe apply force on a object that is at rest to make some change, right? But here there is no force applied, so the object, or else over here the charge, will keep on moving as usual in the straight line itself. Okay, so we need to be very good with these cases. What will happen if they are perpendicular? What will happen if they are parallel, anti-parallel? We should know if they are perpendicular, V and B, that is velocity and magnetic field, they will end up giving us circular paths. If they are parallel, anti-parallel, they will end up traveling in straight line in the surface. So we should know how to judge motion of the particle or motion of the charge, to be specific, in that magnetic field, right? So I keep on reiterating the heading of this topic: force due to a moving charge. You should know this moving charge is entering into a surface that has magnetic field established because of ongoing current in it. So in this situation, how your force will be coming into the scenario? It will come into the scenario with the help of V cross B. So you should know that velocity and magnetic field will give you the information of direction of this force. See the heading properly. So when this force direction is known to you, at that point of time only you can judge the path of the charge. I hope now I'm clear, right? So this is how we are judging path with the information of force, which is again relying on velocity and magnetic field. So still, if people are yet trying to struggle about imagining how this would look like, I have already told you, let's have notes beside you to actually understand how the imagination will work, right? You should also draw it along with me instead of just sitting without notes. That you can see that over here when I say V and B are perpendicular, right? You know that this is velocity of the charge, Q, which is approaching, right? So at that time we have taken one time B as inside and one time B as outside. Okay, so B and V in this case are what? They are perpendicular, right? And in this case, if you see, basically what is happening, you can say, if your B, that means magnetic field is coming outside, your velocity of the charge is also actually coming outside, or B and V are anti-parallel. So like this, forming 180, forming 0, right? So these are the imaginations that you would have to keep in place to understand how the procedure works. I'm going to count this as case 1, I'm going to count this as case 2, okay, and then start the next explanation. Yes, so after understanding these two, now you know that in the first case, basically the result, the path is going to be circular but not uniform. In the second case, it is straight, right? Because the force itself is zero, due to which there is no disturbance. It keeps on moving with that force. It means the charge over here, right? And now comes the case 3. At that point of time, I'm considering a very large size large size conductor, and I'm assuming the magnetic field is going inside, right? So with this, I am actually seeing the charge is already inside the, this is very important to note, the charge is already inside the surface. It is not approaching, not going through transient period, nothing. It is already, you can say, within, it is present within the, it is existing within the surface of the conductor. And this conductor is also exhibiting magnetic field due to its current carrying nature, right? So in this case, since this is a large surface, this surface is a large surface, the charge is already present inside. Let's understand how it works. This charge will actually follow a circular path, okay, that I have drawn. So this circular path looks like this, the white pen that I've used, white color I've used over there. And so here you can see that I'm just taking example. Yeah, so if you see, for example, this is the velocity, right? So can you tell me at this point where is the force going towards? So use your right hand four fingers in the direction of force, right? Curl them towards inside of the screen, which is the direction of magnetic field, and then you will be able to find the force direction, which is actually going upwards, right? Over here. So let me ask you over here, if I ask you, this is the velocity, can you tell me, if you use your four fingers across this velocity and curl them towards the inside of the screen or inside of the book, if you're drawing it along with me, at that point of time, your force, where is your force? It is again going towards the center. Over here also you will see that this is velocity, this is force. Over here also you will see this is velocity, this is force. So we end up getting a scenario where the charge is actually having the force which is going or concentrating towards the center of the circle, right? So during this, what we obtain is, so you can see all these tangents are basically giving me what? They are giving me direction of velocity, and the force is towards the center. Even if you want to measure it here, this is velocity, right? You keep your four fingers towards this and curl them inside the screen, I mean towards the inside, you will end up getting the thumb direction that is upwards, right? So all the times, everywhere, tangentially, you will be able to see throughout the circle, the force is acting towards the center. So that means here also the path is circular. But most importantly, since the charge was already inside the surface, you will be observing that this magnitude of this velocity remains constant. So V magnitude was same. I know V direction is changing, that I understand, because it's tangential. Over here it's this way, 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 over here it's this way. I get that. But what I'm trying to say is the value of that magnitude of velocity remains the same because of the charge being already present in the large sized surface that is carrying current and exhibiting magnetic effect, right? So at that point of time, this circular motion will become UCM, which is uniform circular motion, okay, because it is having constant speed. I hope you understand that when magnitude of velocity is same, what I'm trying to say, velocity is a vector, but if magnitude of velocity is same means I'm talking about speed. So speed is not changing, direction is changing. So that is exactly the characteristic of UCM, grade 9 physics, CBSE, right? Which means now this force is actually acting towards the center, right? This force, if you see on this circle, I'm going to draw it again. On this circle, if you see, this has become an oval. I need some more space. Yeah, so on this circle, if I see velocity is tangential with the same magnitude, and most importantly, my force is always going towards the center, right? So this will become what? This will become again centripetal force. That means it is acting towards the center. This is centripetal force over here in this case, because of the charge already being inside. Don't forget it. It's not approaching, it is already inside. So now I can say that centripetal force is actually equal to magnetic force in this case, right? Because it is UCM, uniform circular motion in this case. That means the charge is actually traveling with constant speed but definitely changing directions, right? So centripetal force, grade 11 formula, chapter 5, work per energy during friction, is mv square by r being the radius, and fb I think you've just learnt with me now, it is qvb, right? Obviously the vector version of the formula, right? The scalar version is q v b sine theta. I'm taking the vector version. So if I take this, I'll be able to get r is equals to mv by qb. Correct me if I'm wrong. So this is the radius. This radius also remains constant because the charge force is acting towards the center of the large surface, right? So the radius also remains constant. It is mv by qb throughout. It's a very important formula, help us solving a lot of numericals as well. So here you can see different formulas of radius. So sometimes in numericals you have different variables given to you, right? And you will have to end up measuring the radius. So mv by qb is what you've just seen. Again in grade 9 your mv is called as momentum, right? While teaching you the second law of Newton. So it becomes p, because I hope you know p is equals to mv. P is momentum used in second law. This is m and v, right? So this is another formula of R I wanted to note down in your book. So R itself is having 4 different formulas, right? So just to reiterate one more thing, this is del V, right? This is not velocity, this is potential. So don't confuse with that, write it in your notes properly. So 4 different formulas: R is equals to mv by qb, R is equals to p by qb, R is equals to under root 2m into ke, that is kinetic energy, divided by qb. R is equals to under root 2m q into del v. Del v is potential, it's necessarily potential difference, chapter number 2 electrostatics, that is potential and capacitance chapter, right? Divided by qb. So overall you can just see that the denominators are matching, they are same, qb itself. Something that changes is the numerator. So in the first formula it's mv, in the second formula you know mv is called as momentum, so it's p. In the second formula it is 2m into ke, and then instead of ke it is q into del v. That means charge into potential difference. Okay, so these are different formulas of R. All of them should be there in your notebooks. We need to solve numericals with the help of these, so try to collect all of them together. So when the charge is traveling in uniform circular motion, it will also have its time period, right? So we need to know the formula of time period as well, which is 2 pi m by q into b. Okay, m is mass of the charge, q is magnitude, and b is the magnetic field, right? Pi 2 and 2 pi is the constant basically, and you know frequency is equals to 1 by t, so this formula will just be the reciprocation itself, that is qb by 2 pi m, right? And the last one is, sometimes they do ask you about angular frequency as well, chapter number 6 grade 11. You know angular frequency is denoted with omega. Omega is 2 pi f, so you can multiply this f and let me know if this is right or wrong. qb by m is what you can measure, right? So these three formulas we need over here: T, frequency, omega, these three. Along with these three, four different formulas of the radius as well. So four formulas of radius and three different formulas as well. These are seven formulas for the special case. The special case is the case where your charge is already present inside the large surface that is having or exhibiting magnetic field because it's current carrying nature. It's going through uniform circular motion. That means the speed is constant, direction of velocity are changing. Okay, so this is a very special case for the numericals that we will solve. Fine. So there are three cases that we have learned so far. I will just wrap them up in the easiest possible way now. Case 1, where you would have seen that V and B are perpendicular, right? At that point of time, the charge will go in a circular path. When V and B are parallel, that means 0 degree, or else anti-parallel, what will happen? It will take a straight path while entering in the surface, right? And then next one is, what if the charge itself is inside the surface? That is very important. At that time, it will be uniform circular motion. Four formulas of your R and three formulas otherwise, right? So these are the three cases that we have discussed. Again, going to the heading, these are telling us about force which is due to a moving charge. These are the different possibilities that a charge can undergo when it is interacting with the magnetic field. Then comes here comes case 4. So in this case, the charge is actually projected intentionally at an angle of theta, right? So this is what we are discussing. So for example, um, this is the direction of magnetic field, and suppose this is the charge q, right? So this is actually with respect to the plane, you can just say that it is projected with some angle theta. Okay, so you know that this is the velocity at this point of time of this charge, and this is the resulting velocity, right? So whenever you have resulting velocities at that time, you can always resolve the components using chapter 4 grade 11, right? So basically what will happen is, you will have two components, one is this and one is this. Close component to theta will be cos component, right? Far away component to theta will be sine component. So I will say that over here, this is how my sine theta and cos theta components will be there. Perpendicular component is sine theta, and parallel component is cos theta, right? So how will the charge resolve? I mean, how will the charge travel in this case? So in this case, the charge will travel like this. Basically, it will travel, how do I explain you? So see, perpendicular component is sine theta, right? Parallel component is cos theta, correct? So it will travel in both the directions. That means it will travel like this. So this shape is called as helical, right? So it will travel in a helical path whenever you are projecting the charge with an intentional angle of theta. Okay, that means it is traveling in both the directions, right? It will travel in a helical path, and you can get to know about x direction over here as well. So for example, so from one turn to another turn, I'll use yellow. From one turn to another turn, the distance between the helical turns is the pitch basically. Okay, that means this is the x-axis direction, right? So that is distance traveled in x-axis direction, correct? So that will be is equals to v cos theta, from where we have taken it, into the time that the charge is taking to travel. Okay, so this formula can be used in order to measure the distance traveled by the charge in the helical path. Okay, in case 4, when we are intentionally projecting the charge at an angle theta of our choice. And then instead of this t, you can also substitute 2 pi m by qb, right? That is also doable. We have seen this formula in the previous cases. That is also can be substituted here, and you know the radius as well, right? Radius formulas that we have discussed so far. And radius formula for this case will be m into velocity component that is perpendicular divided by qb. Okay, so you must be knowing that we have taken this formula from the previous discussion only, where r was equals to mv by qb, right? We have just taken this velocity perpendicular component. You know, perpendicular component over here is sine theta, so we can just replace it with sine theta. So this becomes your r formula. So I hope you're noting it down, so that it doesn't all collect it at once and confuse you. This is r, and previous one was the distance of the pitch for this. Okay, so let's jot down all the four cases at once. In the first case, we have seen that velocity and magnetic field are perpendicular, and the charge is expected to go in a circular path but not uniform. In the second case, you have seen perpendicular. In the second case, you have seen VB being parallel or anti-parallel. This is a symbol I use for parallel, okay? Don't confuse. So in this case, you have seen that it is traveling, the charge is traveling a straight line, basically. Straight line path. And then in the third case, you would have seen that it is traveling, I mean, the charge is inside. It's a special case. At that time, it is traveling in uniform circular motion, UCM, right? Where the speed doesn't change, it remains constant, and velocity is changing in terms of direction, right? And then the fourth case, you're choosing an angle theta and you're projecting the charge, right? So in this case, you'll be able to see that the path is helical. So can you see the range of motion that the charge is experiencing? Straight, circular, uniform circular, helical. So these all path predictions are very important for us to understand how a charge will act, okay, whenever it is kept in a pre-existing magnetic field. Okay. Next discussion is about Lorentz force. So it is basically the vector sum. Okay, that means the total force. Obviously, now you would have understood that there are two forces that are existing, right? You remember in chapter 1 we have studied about Fe. That means the electric field force. In this chapter you are studying about Fb. That is magnetic field force, right? So in your first chapter that was about electric charges and fields, your Fe was equals to QE, correct? F was aligning, that means force on the positive charge was aligning to the force of the direction of the electric field, because it's plus QE, and for negative charge it will oppose, is what we have discussed. In this chapter you have understood that FB will be is equals to Q V dash cross B dash. So with this, we have to cumulate both these forces together, and this is possible with the help of Lorentz force. Okay, so what Lorentz force does is it gives you the F net. Okay, that is QE plus Q B dash cross B dash. Okay, so this is actually your FE plus FB. So take this down, right? So this was covered in chapter 1. This is covered in chapter 4. So these two collectively are called as Lorentz force. So from this discussion of Lorentz force, you must be wondering that over here there are two fields that are involved, right? Electric field and magnetic field. As you can see, electric field and magnetic field. So when these two fields are involved, we should know how we can actually imagine them, right? So let's try to do that. Yeah. So when you see, for example, you have E and B, right? I'm just assuming they're perpendicular to each other. So how will that look like? For example, you have a positive plate and then you have a negative plate, just like a capacitor basically. So this is a completely positive plate. this one's a negative plate, right? So here if I take a charge plus q, for that you should know the electric field. So let's assume you know from plus it goes away, from negative it approaches towards. So this is the electric field that I'm taking, right? And your charge with blue color is actually entering the path, right? So when it is entering the path, at that time I want you to explain me on which axis which variable will be taken in this scenario, right? You have two variables, you already know. One is e, right? You can take this on y axis. One is b, you can take this on z axis, and your velocity of this charge will be taken on x axis. So basically this will be your velocity, this y-axis will be your electric field, and this will be your magnetic field. This representation is the most important thing for us to understand in this chapter, because we are actually seeing how Lorentz force concept can be imagined, and it can be further checked and evaluated. So yeah, so here on x-axis is where your charge is traveling, and when it travels, I'm just taking I've already taken the electric field, you can see from positive to negative. I should also talk about the magnetic field. So I'm just assuming the magnetic field is going inside. So if the magnetic field is going inside, now what will happen? You will ask me that since we have to compare electric field and magnetic field, right? So some prerequisite or some condition should be given to us. So let me give you a condition. Let's assume condition A. You can write it with me along with me in your notes as well. Let's assume case number one, that is electric field is less than magnetic field, or what I meant is magnetic field is stronger. So if the magnetic field is stronger, what will happen to this charge? Can you tell? So this charge velocity is let me yeah, so this is its velocity, right? And what will happen is, so I'm taking this for simplicity plus q charge over here, right? So its velocity is like this. I'm just imagining it separately for our understanding. So what will happen is, where is the electric field going? It's plus to minus, so this is the direction, right? And where is the magnetic field going? The magnetic field is going inside, right? Let's use product rule, that is place your four fingers in the direction of velocity and curl them towards the magnetic field which is going inside the screen. So your thumb will direct upwards, so that will be FB, right? And my first case is what? The magnetic field is more than the electric field, right? So my net field will always come downward. So I can draw this again. So the net direction will be towards the magnetic field, right? So I can actually denote it. Actually, it should not be this direction, right? FB is greater, so it should be this direction. So the net should be over here, right? I would have said that it is directing towards here, but that does not make sense, because in our condition FB is greater than FE, right? So it should go towards direction of FB, that is more than FE, right? So it should go towards the top. So you can say that it is FB minus FE, and this is the velocity. So in this case, what will happen is it will travel a parabolic path, and this parabolic path will look like this blue that I'm reflecting over here. Which case is this? Where magnetic field is stronger than electric field. This is the case where we will see that FB minus FE is the sum that is actually towards the top, right? So if you want to change this, and maybe you can talk about FE greater than FB. Now let's talk about B. So in that case, what will happen? Can you tell me? Yeah. So in this case, basically, it will align more towards this direction, because FE is greater, right? So if FE is greater, what will happen at that point? You will see, you will draw the diagram, you will erase this part and you will draw it like this. FE minus FB. So this will become the diagram for the second situation where electric field is stronger, right? And what will be the path? The path will be parabolic here also. It will come like this. So I can draw it like this basically, right? So I hope you know that this corresponds to my first case. First case means FB is stronger than FE. The second one is corresponding to FE stronger than FB, right? So third case that is very usual would be both of them being equal, right? So when both the forces are equal at that point of time, what will happen is both of them will end up giving you constant velocity, right? The net will become zero and the particle will move with constant velocity. And this is exactly the so in this case of constant velocity, where both the forces are equal, electric and magnetic, basically the net force will be zero and the charge will travel at constant velocity, right? So when the charge is traveling at constant velocity, this is how it will look like. Now I've drawn it with yellow. I should have drawn it with blue. So this is the case of Fe is equals to Fb, and in your NCRT also you will see that there is a device with the name of velocity selector that is designed on this basis. So basically you have so many charged particles, right, that are in movement, for example electrons, ions, etc. So from this lot, if I ask you give me the specific speed of particles that have 3000 meters per second, so all of these charged particles will not be at 3000 meters per second, right? But my requirement to you, my ask to you is to give me these particles that have specific speed of 3000 meters per second only. At that time you will use this device, that is velocity selector, that will function on this condition Fe is equals to Fb. Okay, and beside that these three conditions I think I've wrapped up now, and this is all about the Lorentz force discussion that we've had. Also, most importantly, since most of us have completed the chapter of ray optics, you remember in ray optics the second part of the chapter was about optical instruments, right? So in that optical instrument, these conditions, that means this velocity selector is also having an application in electron microscopy. So I want you to explore this on internet to check how electron microscopy works with this condition of velocity selector and come up with your answers. Maybe discuss it with me at school. So adding up one more analysis over here, I have seen a formula where they have asked us about time spent by the charge in magnetic field at some angle theta. That means basically the entry of the charge in the pre-existing magnetic field surface has been done at an angle theta. Obviously the exit will also be done at an angle theta itself. So T in that condition would be 2 pi m by 4 qb. Include this formula as well in your formula page of this chapter. So this is force in a current carrying conductor, or else in a current carrying rod actually. Correct this heading. So basically you know that for a single charge, in the beginning of this part of recorded lecture we have seen that this is the force, right? Vectorial form for a single charge, right? So now the question is how will it change for a complete current carrying rod, because this one for single charge cannot be applied to a rod, right? So for single charge there must be some other provision is what we are talking about. So let's take this rod. Basically if you take it, so basically what I'm telling is you have, let me just draw a proper diagram. Yes, so when you take this rod, maybe you can take n over here. So n is basically number of electrons, and what is small n? Small n is basically charge per unit volume. Okay, and this rod obviously has some length L and area of cross section A. So if you have that, you can count up the formula of I guess the formula goes like this. It will be F is equals to I L bar cross B bar. So I want to tell you that L is the displacement length, right? And you can also know the magnitude of F basically, which will be F will be equal to IBL sine theta. So this is one formula, this is another one, right? These two are very important because these two will help us understand. I mean, one is vectorial, one is magnitude, obviously it's the same. Force in the rod, so you can't apply this formula anymore because this is only for single charge, but here when you're considering the complete rod as such, you will be applying these formulas. Okay, now the next thing that we will be discussing is going to be 1 ampere of current. So I know most of us would have learned this in grade 10 itself in the chapter electricity, right? Where SI unit was ampere and then it was taught to you in a certain way. But now we are upgrading this with help of magnetic field, since we have understood that this presence of magnetic field is actually created or evidently seen by the pre-existence of electric field, right? So there is current before the magnetism is produced. So what we do is we try to consider, I will just write it for you once, then you can take it in your notes. So here we are just upgrading, right? 1 amp of current. So it's the current that flows through two parallel wires. So these two parallel wires, you can take them in one, I1 is flowing and in another I2 is flowing, and they're parallel to each other. They're separated by what sort of distance? 1 meter of distance in vacuum. That is the medium that they're talking about. 1 meter is the distance between the two parallel wires, and it's producing a force of 2 into 10 power minus 7 newtons. So on a unit length of wire, so basically if you consider 1 unit length of a wire, of any wire of this parallel configuration, this is the force that will be exhibited on them. So that is actually 1 amp of current. So in 12th grade we see assertions based on 1 ampere of current as well, where you cannot use that old way of defining ampere of grade 10, because their magnetism was not a part of your curriculum taught to you in the chapter of electricity in grade 10. But here in 12th, when you're studying chapter 4, which is moving charges and magnetism, this is a very important definition that we should know. 1 amp of current is actually the current which is flowing between these two parallel wires. So this is parallel wire 1 and 2, so it's flowing between, right? So sorry, it's not flowing between, it's flowing through. Okay, so it's flowing through these wires. Basically I'm just showing you the current, and these are separated with some sort of distance of 1 meter, and it's producing a force of 2 into 10 to the power of minus 7 newtons on unit length of wire. So that means on 1 unit length of wire, what is the force that is exhibiting is equals to 2 multiplied 10 power minus 7 newtons. In your textbooks you will see that this is force again on a unit length, right? F by L, which is equals to mu naught I1 I2. That means I1 current in first wire, I2 current in second wire. These two wires are actually parallel to each other, divided by 2 pi r. Okay, so that also they would have given in your NCERT textbook. You can check it out, and that's how you define 1 ampere of current. It's the modified definition. So now we are discussing about torque on a conductor, and this conductor will obviously be carrying current, which is why magnetic field will be exhibited by it or induced by it, right? So let's understand, torque is something you would have also seen in your chapter 1 as well, right? In chapter 2 as well, where we were discussing different things, so first two chapters, if you see, electric charges and fields, electrostatic potential and capacitance, that is from electrostatics, right? These two chapters, that is chapter 4 and 5, these are from magnetostatics. So they talk about magnetics, and besides statics they also talk about movement as well, right? So in these chapters when you're studying about torque, you would have seen that quantities are actually replicating over here as well. So what does that mean? So for example, if you take dipole moment, right? I'm just going off the topic. So if you have dipole moment, minus to plus is the direction, right, from negative to the positive. So dipole moment is telling us the strength of a dipole, right? So the quantity is q into 2l. In the same way, we will also have a magnetic dipole as well, right? So you can check about magnetic dipole in your textbooks as well. Do check it in your ncrt. All I meant to say is those electrostatics will replicate in this magnetostatics as well, right? Now we just have these two magnets, obviously dipoles, and when we have this, this is how your magnetic field is traveling. So in this we are placing a coil basically. So when you place a coil, what you see is, for example, you can label it. Yeah, so I'll just consider one of the directions. Consider it as one of the directions because we have to start explaining this. So one direction is that we need, right? So let's assume this yellow is the direction. I'm considering clockwise direction, right? So this clockwise direction is the current direction basically. So as I have considered the magnetic field which is going from right to left to right, sorry, right? Yeah. So left to right, as you can see, and then current on the AB phase, if I'm considering the AB side of the coil, it is going upwards, correct? So this is the direction of magnetic field, this is the direction of current. So which length are we considering of the coil? We're considering AB length of the coil, right? And if you use product rule, that is L cross B, place your four fingers in the direction of L. So basically L is a scalar, right? But when the current is measuring through L, it becomes a vector. So basically I is flowing through this AB phase, right? So now it becomes like a vector. So can you place your four fingers in direction of L and curl them towards B, which is towards the right? So can you tell me where is your thumb directing? I will repeat. You will have to use the product rule for L cross B, right, to understand the direction of force. To determine the direction of force, we need to understand how L cross B will be used. And for using L cross B, what I'm telling you is this L, the length vector, is actually a scalar to our understandings, but since it is length of the conductor or the coil, which is placed between the two poles of the magnet over here, right, in this discussion, and you're able to see that throughout this procedure, what we are doing is current is flowing. So current is flowing from B to A is what I have taken in my explanation, and magnetic field is going from left to right. So curl your fingers, four fingers of your right hand, from L towards B, and then tell me where is your thumb locating. You can pause the recorded lecture and then check. So you'll be able to see that the force is inwards, right? So if the force is inwards, that is the direction of the force. So I can say the force is inwards on the AB phase, right? Now, can you come on this CD phase? The magnetic field is as usual, it's going from left to right. So that means this will remain the same from left to right, correct? But then something is changing over here. That is the direction of the L, that is direction of current. Because now it is not going upwards, it's going downwards. So can you use your hand in the reverse direction, and then you'll be able to see that B is going left to right and I is going from top to bottom, which is downwards. At that point of time, your force will come outwards, your thumb will direct outwards. So this is the direction of force for which phase? CD phase. And this is the direction of force for which phase? AB phase. We have used L cross B to determine direction of F using the cross product rule of grade 11. And because the force going inwards on face AB of the coil and coming outwards on face CD of the coil, how will it rotate for now? It will almost look like it will go inward, right? And when it goes inward, this is how it will look like. I've just tried to draw this white right now, correct? So I will just say that your AB that has gone inward and CD that has come outward, right? So this would be AB, this would be CD, right? Because on AB, you know how you have used L cross B, that has explained us that force is inwards, and then on CD if you use L cross B, that has shown us that the force is outwards, which is why I'm reflecting CD, if you can see it properly, right? This CD, right? I'm reflecting this CD face on top and AB phase at the bottom, right? Because this movement or the torque or the basic rotation has taken place due to the magnetic field, which is going from left to right, and also the direction of current in the coil ABCD that we have considered, right? So you know that F is equals to, it's BIL sine theta, right? So in both the things, let it be face AB of the coil or face CD of the coil, uh, theta is necessarily 90 itself, right? So I can say that force on the face AB, force on the face CD, if I use 90 degree over here, it will end up giving me BIL itself, right? Now this is the explanation for phase A, B and CD, but how about phase A, D and BC? So they will end up having a different explanation altogether, right? If I clear this part, um, yeah, so this is the movement right now, correct? So if I clear this path, can you see that over here, your yellow is the magnetic field from the beginning, right? So when your yellow is the magnetic field and white is basically the coil, right? So there is some sort of angle that's forming over here. So we have to consider this angle as well for these faces only, that is AD and BC, because AB and CD is done and AD and BC are yet to be discussed. Assuming we don't know the angle number, so it's alpha, and so your FAD will be obviously BI, so that will also be BIL sine alpha, right? Because alpha is something that we are trying to consider. Okay, so the net force, if you see, will be zero throughout the situation. But then even though the net force is zero, the forces on the sides can still produce a torque, right? Because chapter 6 grade 11 tells you that torque is what? It's the cousin of force, right? Cousin is from linear family, torque is from rotational family. So torque is basically a rotation equivalent of force, right? So even if the force, net force is zero, it will still end up producing torque, is what we are trying to explain over here. And the forces on sides 1 and 3, or maybe like 2 or 4, whatever it is, A B C D we have taken, it creates a torque, and this torque tends to rotate the coil, and these torques add up to produce a net torque on the coil, right? And obviously the torque that we are considering will be maximum when the plane of the coil is parallel to the magnetic field, and it will be zero when the plane of the coil is perpendicular to the magnetic field, right? Perpendicular, you know, when it's at rest, and it will be parallel, giving you the maximum torque. So that is the thing. So rectangular current carrying coil placed in a uniform magnetic field will be experiencing a torque, because the force on its sides will create a rotational effect, is what we are trying to explain. It does not experience net force, obviously, because net force is going to be zero. Okay, because you know that forces on opposite sides are equal and opposite in nature, resulting in cancellation, but then still torque will be generated, is what we are trying to explain. So you will get your tau net which will be equal to I BA sine theta, okay, or else sine alpha, because I've taken alpha over here. So I will rewrite this angle as theta itself, or else you can take sine alpha over here, it's the same. Okay, I is current, B is magnetic field, A is the area, and theta is the angle that this phase and this phase will undergo, right? Because they are the rotational widths, right? So this is one way of representing this tau net. For number of turns, you can just multiply this formula with n, and so you will have magnetic moment, which is basically I into A, current into area. Okay. So for a loop, the current into area, just like how you had electric dipole in chapter 1, right? So we can, instead of using I and A, we can just use M, and you can also call it as MB sine theta, or else for n turn NMB sine theta. That also works. So cross product form, we can just write it simply as tau is equals to M cross B, right? So if you know the directions of M and B, you can end up getting the fingers curled towards B from 4 fingers from M, and you can get the direction of torque. That is it. So just now you have understood how a rectangular coil or a basic coil will undergo or will exhibit torque even when the forces are ending up or cancelling each other when kept in a magnetic field. On that only we have a device application in your NCRT, which is moving coil galvanometer. So already you have ammeters in the lab, right? So they actually measure the current, but then galvanometer is going to detect the current. This word is very important. It's going to detect the current. That means it's going to evidently tell us the presence of the current and also measure it. That is a secondary purpose. Small currents, these are not huge large level currents, these are very small amount of currents, 0.0001 amp, right? So ammeter will not be accurate in such situations where we would want to detect the current. The presence of current is not actually the whole purpose of using an ammeter, because it is calculating the considerable amount of currents. But galvanometer is based upon just the it's the application that is based upon the principle that we have studied as to how a coil will behave when kept in a magnetic field. So detection is very important over here, is what I'm trying to say. So your general laboratory ammeters that you use, for example, they will measure 2 amp, 3 amp. So this is actually considerable amount of current. I'm telling you what will happen if you have to measure 2 into 10 power minus 6 amp, that is microamps, right? Mu amp is what I'm telling about. So these kind of small minute currents will be actually measured with the help of galvanometer. So in our school lab, you'll be able to see that if you want to measure it up till milliamps, okay, you can use this because it's a very sensitive amount of current, right? A very, very, very less amount of current, which a general ammeter will not be measuring. So this sensitive amount of current will be measured with the help of galvanometer. So that's the application and usage. So the construction of galvanometer is done with the help of radial poles of the magnet. Okay, so it's not the usual poles like this what we have drawn, right? These are radial poles. So what's the purpose of having radial poles also? I will explain. This is actually the place of coil in the previous explanation, right? This is soft iron. Okay, so you're using this soft iron over here, and what you will do is you will see that this is how your field will flow through this coil, right? And this will be connected to a spring. Okay, and this spring will be connected to a pointer on the scale in your lab to tell you the detections of the currents, right? So this is something that you will visibly see with your human eye, but then this is the mechanism that is going at the back end. So how will it work? So there is this coil which is wrapped on the soft iron, right? So current will flow through it. It will produce torque like the previous explanation, correct? And then it will, exhibit some sort of pull on the spring, and with that pull, the device will show you the detection on these readings on the scale to where it is going. So that is the working of the instrument. So the principle that you have studied, which is basically when a coil is kept between the the magnetic poles, or in the presence of magnetic field, it ends up experiencing torque, right? So this torque only is going to produce pull on the spring. So that pull is generated by the torque, right? Torque, the small movements, is what we have discussed in the previous discussion. So tension is caused in the spring, okay? Torsional strain you will see, and this is zero, and you will see the values. I'll show it to you in the lab. You can also explore the galvanometer in the lab. It will help you to detect the presence of current. And also, reason of taking soft iron is that, when we switch it off, or when we are not using the moving coil galvanometer, at that point of time we are also looking that it should demagnetize easily, so that it should not be exhibiting any more magnetism or torque any further, right? So we choose a substance in the place of coil which is demagnetizing, readily demagnetized, right? So that's why we have chosen soft iron. We do not want to choose anything like cast iron, or there are other different forms of irons as well, because they don't demagnetize easily. So the challenges of demagnetizing as well, so that is why we end up picking up soft iron for this device. So if you see the formula of torque, it would be B I N A sine theta, is what we have discussed, right? So to produce constant torque, if we take theta as 90, that is, it will end up at one value. So we don't have to consider sine anymore. And this is why radial directions are taken, so that it ends up actually making perpendicular angles over here. So how much will this, when current is passed through the soft iron, what will happen at that point of time? You will end up seeing the torque, and then that will create a torsional strain, right? And that will deflect our pointer. So what is happening at that point of time? How much is the deflection of the pointer? Basically, I'm getting to know with the help of phi. Okay, so what I'm trying to say is the phi value is directly proportional to I. So deflection will be more only when the current passed is more. Okay, so that is one thing that we should know from here. And it comes up, if you see your NCRT, you will have this expression that is NBA by K into I. So from here itself, I'm drawing this conclusion. So phi is your angular deflection, which is directly proportional to the current that you provide it. And you'll have to understand that the spring is going to provide a counter torque, right? So that counter torque is basically K phi. You can see it in your textbooks, and this is the counter torque that is going to balance the magnetic torque. The magnetic torque is going to be BINA, right? BINA is going to be the magnetic torque, and the counter torque, which will be provided by the spring, obviously, will be K phi. So these are the two. So this will only result into a steady angular deflection, right? Because steady angular deflection is something that you need in order to conclude whether your presence of current is there or not when you're using galvanometer in the lab. So more amount of current given will produce more amount of deflection or twisting of the pointer, basically. So here there are two important things to discuss. One is current sensitivity. So if you see, the name itself suggests us that the deflection that is produced in the galvanometer when a unit current is flowing through it. So it is denoted by IS. So basically IS is equals to phi by I. So as I told you, it's the deflection, right? This is the deflection. It is produced in the galvanometer, obviously, when a unit current flows through it. So that is the current sensitivity. Okay, so you will also see a similar expression in your textbook, which is NBA by K, right? And the unit of current sensitivity would be radian per ampere. Okay, it's radian per ampere, or else sometimes it is also called as division per ampere based upon the textbooks that we're using. But you can just check with this, that should be fine. Then after current sensitivity, the next is voltage sensitivity, which is Vs. So Vs is again, as you would have guessed it, phi by IR. So that means the deflection produced in the galvanometer when a unit voltage is applied across the two terminals of the galvanometer. In your book you will also see NBA by KR for this, and the thing, the SI unit will be radian by volts, right? Because you know IR according to ohms is what? It is V itself. So they're using V over here. Okay. Sometimes in different textbook you will also see division per volt, but you can use this. That should be fine. Okay. So this is current sensitivity and voltage sensitivity parameters, which are important for us to discuss while constructing the galvanometer. And now, if I ask you, after discussing the moving coil galvanometer, means it is used for detecting the presence of the current, right? And also for measuring very small amount of currents, which are very difficult to measure by a ammeter. So because ammeter is always measuring considerable currents, right? So can I say ammeter is a low resistance galvanometer? You can say that ammeter can be imagined as a low resistance galvanometer. So ammeter is essentially a galvanometer with a low value shunt resistor, which is connected in parallel to it, right? So you know this allows it to measure the current accurately, as we have used it in labs before in our previous classes, and also one more thing is to make a moving coil galvanometer into an ammeter. What do you think you have to do? So you will have to add up a shunt to this moving coil galvanometer. Shunt means if any resistor is connected in parallel, we call it as a shunt. Okay. So you know that galvanometer is sensitive device. It gives full scale deflection for a current of milliamps, right? That is 10 power minus 3. So for measuring currents, galvanometer has to be connected in series as it has a large resistance that will change the value of the current in the circuit. So which becomes a difficulty for us, right? So what we will do is to overcome this problem, we will shunt it with a um, resistor so that most of the current can pass through this shunt is what we are trying to see over here. Okay. So while doing that, also one more thing that we have to note down, as you can see, this is galvanometer, this is resistor added in shunt, that means in parallel, right? And we have to make sure that most of the current passes through this resistor only so that it can become an ammeter. What is our goal? Our goal is to convert a moving coil galvanometer into an ammeter. And in your book you will see RS is given as IG, I minus IG, RA. So in this expression, you can see RS is what? It's the resistance of the shunt. So that means they will ask you what value of shunt resistance should be added to this galvanometer to make it into a ammeter, right? So IG is what? It is current through galvanometer. I is the total current. IG is again current through galvanometer. RA is the resistance through this. RA is going to be the galvanometer resistance, okay? Or you can also denote it by RG. I mean, I think to me, RG, writing RG over here makes more sense, right? So this is a very small value of RS should be included in that parallel connection resistor to the moving coil galvanometer in order to make it an ammeter. So again, to convert it into a voltmeter, first of all, we need to understand that voltmeter is what? It is a high resistance galvanometer, right? You know, voltmeter is basically used to measure potential difference between 2 points of a circuit in volts, SI unit, right? So galvanometer can be converted into voltmeter. All that we have to do is we will connect a high resistance in series, okay, with the galvanometer so that it draws a small current. Otherwise, voltage measurement will disturb, right? Voltage measurement will disturb the original setup by an amount that is very large. So for that, series connected the resistor to make the moving coil galvanometer into a voltmeter. The value would be V by Ig minus Rg. So I hope you know the parameters now, right? So this is the so this R would be the resistance of the um, series connection of the resistor that you are joining with the moving coil galvanometer to make it a voltmeter, right? And okay, so again, this is resistance of the galvanometer, this is voltmeter's voltage, this is current of galvanometer, and this is the desirable resistance that you will add in series with the moving coil galvanometer to make it a voltmeter. With this, we are done with the last part of this chapter, and we have wrapped up the chapter 4 with this recorded part. Just to give you a gist of what we have learned is it's about moving charges and magnetism. We've started from Biot-Savart's law, understood its applications, then continued with Ampere's circuital law, then also have its own applications. Then we further moved into forces, right? Forces on a charge in a magnetic field. So we've realized that force on a single charge also, and also on a full-fledged rod as well. Then we've come across a few cases regarding this, and continuing with Lorentz force. Lorentz force, again, we've seen 3 different cases. We've also seen the application of velocity selector, I guess, right? And then continuing with moving coil galvanometer, right? Converting it into a voltmeter and an ammeter. And what are the conditions? You will have to, in order to convert it into an ammeter, you will have to connect a shunt resistor. You know the value, it's given by the formula. And then we have an expression to convert the galvanometer into a voltmeter as well. You will have to connect this value of resistor into series. So with this, we are done with this chapter.